Okay, this is section 3.8, and 3.8 are the inverse trigonometric functions. And so this is the notes portion of this, this section, so we're going to observe the no technology. In other words, just kind of keep focused on the video. Try not to let anything else that comes into the screen disturb that. So we're talking about inverse trig functions. So before we start talking about inverse trig functions, let's start with just regular inverse functions. And this is not in your notes. This comes from the chapter 1, the prerequisite chapter, when we talked about inverse function. So we're just going to kind of review this. If you want more notes on it, go back to your Unit 1 notes. So let's start with a function. Y equals 2 over 5x plus 1. So we know it's a line. Got slope of 2/5 and intercept of 1. So here's that line. We know when we're talking about an inverse that we swap the x's and the y's and then we solve for y. So I'm going to swap my x and my y, and then I'm going to go ahead and solve for y. I'm going to subtract 1 from both sides. I'm going to multiply by this reciprocal. So I subtracted 1, multiplied by 5/2. So here is your inverse function. So if we graph this one, we get a slope of 5/2, and it's got an intercept of -2.5, it looks like. So there's -2.5, and then we go up 5, right 2. So there's that inverse. So if these are the inverse of one another, in other words, where there's an x, now there's a y, if we think about it, if we look at this point is 0, 1, and its inverse would be 1, 0. So, so those points are inverses of one another. Notice one's on one line, one's on the other. But if you remember back to the prerequisite chapter, that inverses have a line of symmetry, and that line of symmetry is the line y equals x. So if we would fold the screen along the screen line, then the blue line would fall on top of the red line. So that's the idea of an inverse function. So each trig function has an inverse. We have an inverse sine, an inverse cosine, an inverse tangent, an inverse cotangent, inverse secant, and an inverse cosecant. Unfortunately, to determine the derivative is really kind of beyond the scope of this class. So what we do is we give you the derivatives, which look really interesting, I guess, to say the least. And then we, with this function and its inverse, we practice things like the chain rule and stuff like that. So when you're looking at these obviously these look really kind of convoluted and strange. And but they have one pattern, if you notice, and that is they have something that looks kind of like a Pythagorean pattern, like 1 minus u squared, or 1 squared minus u squared. If I have a minus sign, and you think about like Pythagorean's theorem, this, and then I have a square root here. This is like hypotenuse minus leg square root sort of thing. So, but all of them, if you notice, the denominators have this Pythagorean sort of pattern. And that's part of the reason on how you solve for them. But again, that's beyond the scope of the class. So if we look at these derivatives, about the only thing you can do is inverse sine and inverse cosine look the same. They're 1 over 1 minus u squared and the square root of that. The cosine is just negative. So if we think about derivatives of regular trig functions, when we took the cosine, we get a negative sign. So notice that negative kind of follows the inverse cosine as well. Tangent doesn't have a radical, it just has 1 plus u squared. So this is like leg squared plus leg squared. And then cotangent, if you notice, it's just the negative of that. Secant is kind of even more unusual looking. It has an absolute value of u, and for reasons that just go beyond that. Secant and cosecant are not too commonly used. Usually it's these four that are used the most. But like I said, unfortunately, we're just going to work with them. We're not really going to figure out where they came from like we did with other derivatives. Okay, so let's just try this concept of an inverse trig function with looking at their sketches, kind of like we did with the regular functions. So let's start with the function like sine x. So there's our sine x. We're going to swap the x and y's. So in order to do this, swapping the x and y's, we need the function to be 1 to 1. Remember, 1 to 1 means we have one x and absolutely one y. So in other words, the x's and the y's don't ever repeat. And in order to do that, we have to pick a part of the sine curve where we cover the domain and the range. In other words, we cover that whole range from -1 to 1 in part of the domain. So, so sine is defined to be 1 to 1 from -pi/2 to +pi/2. That's where the y's never repeat. So now that we've defined it in this domain, we can swap the x's and y's, and then we can solve for y. And so solving for y here involves taking the inverse sine. So that's where that comes from, and that notation comes from. And the inverse sine looks like this. So the inverse sine we can think of as, for every value of x, what angle does that correspond to? That's kind of how we're looking at that. And so if we look at this then, if we look at this from a line of symmetry standpoint, if we want to get the inverse, we need to reflect this over the line y equals x. So we're going to have to flip it and spin it. And as you can see, when we do that, and we get this graph here, and now I've kind of slid that graph here. Here's the line y equals x again. Here's a line of symmetry. You can see that over that domain from -pi/2 to pi/2, that this inverse sine graph is the mirror image of the regular sine graph. There's that line of symmetry between the two. So that's kind of where the inverse sine comes from. So we see that that's one and the same function. So talking about then the derivative here. So since we know that the inverse defined is here's my domain now, which was my range of my old function, right? My y values went from -1 to 1. Now that's the domain, because with the inverse we swap x's and y's, and our range is now -pi/2 to pi/2. So we have this as our derivative for our sine function, and that's in this domain here from -1 to 1. Notice the domain is -1 to 1 because look at the denominator. Any x value that is outside of that domain is going to make this radical negative, which is something that we can't define. Okay, so that's why we have that domain in the first place. Okay, so let's look at cosine then. So here's our regular cosine curve. Now, our cosine curve is not 1 to 1 in the same domain. Okay, if we look at this, the y's repeat each other. Our cosine curve is 1 to 1 from 0 to pi. That's where we go through all the y values without repeating. So, so here's our y equals cosine x. We're going to swap the x's and y's, and we're going to get our inverse. And that inverse then, if we look at that graphically, we're going to flip it and we're going to spin it. And when we spin it, it looks like that. And so if you think about then the line of symmetry, I think I have it here. Oh, I guess I don't. So I don't go through the line of symmetry there, but that would be our inverse cosine. So again, the domain is from -1 to 1. That's the old range. And our range is now from 0 to pi. And so this is the derivative. And again, that domain has to be from -1 to 1 outside that domain. And we have this radical that would now be negative, which is not defined. So that's why that domain is important. So there's our cosine. And then from those two, we're not going to go through the other four derivatives in terms of their inverses. But as you saw a little bit before, complete with the chain rule, then we have something that looks like this. And the chain rule is really what we're kind of looking at applying with our inverse trig functions. So there's sine, tangent, and secant. Complete with the chain rule, there's cosine, cotangent, and cosecant. And then just a note on the bottom here, the alternative expression for sine inverse, the sine minus 1, we can also call it the arc sine. Those two mean the same thing, and you'll see them used interchangeably. So kind of keep this here at the bottom of the screen kind of in the back of your mind. Those two mean the same thing. Okay, so using the chain rule here is really what we're going after. So if we want the derivative of the inverse sine of 3x, that means we have to take the derivative of the inverse sine, which is this part, and then we have to take the derivative of the inside, which is the 3x. So, so there's our function, and we typically take the inverse sine of u, so we're going to keep in mind that u is just 3x. In other words, wherever I see a u, I'm going to put a 3x. So the derivative then, of course, the derivative of u is just 3. That's this out here. So setting up then the derivative of the inverse sine, like I said, wherever we see a u, we're going to put a 3x. And then here's our du dx. So our derivative then is this. It's 3 over the square root of 1 minus 3x squared. Or you might see this bottom part without brackets as 9x squared. Okay, so that you may or may not see the brackets around that. Let's take a look at tangent, inverse tangent of 2x squared. So there's our function. We call u 2x squared because this derivative is set up for tangent of u. And so everywhere we see a u, we're going to be putting a 2x squared. So let's take the derivative of u. That's 4x. That's our chain rule. This is the derivative of our inside. So our derivative then of inverse tan of 2x squared is 1 over the quantity 1 plus 2x squared, quantity squared, times 4x. And so we could also write that as, bring the 4x on top, because this is the same as being in the top of the fraction. So it's 4x over 1 plus 4x to the fourth. So this is where I wrote it without brackets this time. So there's the derivative of the inverse tangent of 2x squared. Okay, so let's take finding the derivative of the inverse cosine of 1 over x. So again, our 1 over x is our u. That's our inside function, basically. So the derivative of 1 over x, then we got to think of this as x to the minus 1. So it's minus 1 x to the minus 2, or it's minus 1 over x squared. So now we can take a derivative of the inverse cosine. So the derivative of the inverse cosine is minus 1 over the quantity, the square root of 1 minus 1 over x squared, times negative 1 over x squared. Those do not cancel, by the way. One's inside a radical, the other one is not. So simplifying this a little bit, you might see it look like this. So we have negative 1 times negative 1, that's a positive 1. This x squared is in the denominator, so I put this denominator all under one fraction. So it might look something like that. Since we're talking about inverse functions, we also need to talk about, and we're talking about the chain rule, which means we're kind of talking about composite functions. If I kind of go back to this previous screen for a second, these are all composite functions, right? We've got an outside function of inverse cosine and an inside function of 1 over x. If we go back to the screen before that, we've got an outside function of tangent inverse and an inside function of 2x squared. So you can see it, we've got these composite functions. So as long as we're talking about inverses and composites, which is why we have to use the chain rule, then we can talk about taking the derivative of the inverse of a composite, which is kind of a lot to say. But you know, think about taking a function, swapping its x's and y's, and then taking the derivative of that, if that makes sense. So let's take a look at this function. It's x squared. And I'm going to find these 1, 2, 3, 4 things. First thing I'm going to start out by doing is just finding the value of the function at 2. That's what this first thing is saying. The second thing is saying let's find the value of the derivative of the function at 2. So I'm going to have to differentiate it and plug in 2. The next one is saying let's find the inverse of the function. So I'm going to have to swap the x's and y's and solve. And then the last thing is I want to find the derivative when I put the inverse, the derivative of the inverse of the function. So let's start by taking a look at this function. And I'm taking this function at positive values of x. You know that this is a parabola. We work with this function all the time, right? It's a parabola. It looks like this, and it continues to go up on this side of the axis. If you think about that, if we mirrored that about the line y equals x, then we would have a sideways parabola. But the sideways parabola is not a function, right? It doesn't pass the vertical line test. So this restriction in the domain, in other words, restricting it to just the first quadrant, allows this function to be 1 to 1, right? We don't have any repeating y values. And then we can find its inverse. So let's start out by looking at where x is 2, okay? So when x is 2, what is y, right? We're going to plug it in here. So there it is. When x is 2, well, we plug in 2, we square it, we get 4. So there's our function value at 2. Could have asked you that back in Algebra 1. Okay, now let's take the derivative, right? So we come up here to the function, we take our derivative, we get 2x. Evaluate our derivative at 2. So 2 times 2 is 4. So we have a tangent line or a slope of the curve of 4 at this location. And then now we need to find the inverse. So we find the inverse by taking our function and swapping our x's and y's, and then we solve. Okay, so we swapped the x and y's. I'm going to solve for y, so I'm going to square root both sides. And then I'm just going to write it as y equals instead of kind of backwards. So here's my inverse. So what does that function look like on the graph? So that's our inverse, because we know we followed the process to find the inverse. Our inverse looks like this, right? It's that sideways parabola. And so so if you notice, the line of symmetry here will pop up eventually, but that line of symmetry then we can see is y equals x again. So we're going to find the derivative of this inverse function. In other words, we're going to use whatever strategy we need to use here to find the derivative of this function. So think of this as x to the half power. And so there's the inverse. The inverse is x to the half power. Now let's find the derivative of that. So we bring down the half and reduce the power by 1. So here's the derivative of my inverse. So what if I want to evaluate that derivative? And here's rewriting it. I guess I did rewrite it. So, you know, x to the negative half, that means a radical, so a root 2, but in the bottom because the radical is negative. This is all the same stuff here. I just need to change screens. Okay, so now notice I'm taking it at x equals 4. Okay, because it's the inverse. So I can't take it at x equals 2. I have to take it at that y value that corresponds to 2, which is 4. So I have to, in order to look at the inverse of my function, I have to look at x equals 4. So when x equals 4, then y equals 2. So that's that point. And so the value of my inverse at 4 is 2. And so looking at that, we know that's the derivative, so we know that's the slope of the tangent line. And so the derivative then at 4 If we look at the inverse here, the derivative of the inverse, so that was the value of my inverse at 4. Now the derivative of my inverse at 4 is 1/4. So there's the slope of the line that's tangent to the inverse at 4. So if we notice, when my derivative of my original function was 4, the derivative of my inverse function is 1/4. So there's a relationship between those two numbers. And that's really how we can go about finding the derivative of the inverse a little more quickly than all of this solving. So what's the relationship between 4 and 1/4? Well, they happen to be reciprocals of one another. So that being the case, since these are reciprocal, so if you think about it, inverses are swapping the x's and the y's. We can think of x's and y's as like rises and runs, right? The x's are the runs and the y's are the rises. So if 4 is a rise of 4 and a run of 1, then its inverse, if we swap those, would be a rise of 1 and a run of 4. So, so we know that the derivatives then are just reciprocals of one another, which is a nice pattern to see, because then what we can say then is if we have an inverse of a function and we want to evaluate its derivative, then we just take the reciprocal of the derivative of the function at x. So this is allowing us to kind of sidestep all of that math that we just did on this problem. So how do we work with this without having to create this graph? Okay, so this is the derivative of the inverse, and it's evaluated at that y value. And that's what the f of a is. And it's equal to the reciprocal of the derivative of the function. And that's evaluated at the x value. So for instance, typical problem might look like this. If we have a function, when x is equal to 3, y is equal to 5, and we know the derivative at 3 is 6, then the derivative of the inverse at 5, evaluated at the y value, is going to have to be 1/6, the reciprocal of the derivative evaluated at the x value. And so that's kind of how we work with the idea of finding the derivative of composite functions when we're just given values. So our essential question was, how do we incorporate the chain rule into inverse trigonomic functions? And the important thing is that u sub and getting that du dx. So your homework now for today is to, and this is just a one-day unit, so we're done. This is the only homework assignment for this section, is to go ahead and do the day 1 homework in WebAssign, or do the proficiency quiz. Either one would suffice for the requirements for proficiency.